Okay, a little late, sorry about that. All right, so we were, let's see. First of all, midterms aren't yet graded, so don't worry about that just yet. I'll get them graded, and the general consensus was it was a little long, but other than that, not too terribly difficult. Is that about right? Yeah? Okay. So anyone thought it was sort of unfairly difficult and everything else? No? Okay. You can speak up. I won't mock you in front of everyone, I promise.
Well, that's what I expected, but not like absurdly difficult.
Okay. So, alrighty.
I think adding mathematics is very happy.
Yes, it would have also made it like take 15 minutes, but
adding do it in shorthand and then verify.
And then verify by MATLAB. Yeah, well, that's a
One question shorter also would be nice. I could use like another 20, 30 minutes.
yeah.
Even like productive.
Yeah, well, it's okay. I was actually a little surprised that no one finished early, but that was that's usually not entirely unexpected. All right, so we were finishing up the various kinds of controllers we had. So we had proportional gain, which we said was like a spring. We had a pure derivative, which is a zero at the origin, which is adding damping. We had integral control, and we said, well, that's an interesting problem. We said a PD control, pure proportional plus derivative control, gives you 1, 0, which you can move around. And what I've made the case for is that taking the derivative of anything that has high frequency noise on it is going to be a bad thing. So rather than do, well, we'll get back to that one in a second, we have proportional integral control, which is essentially a 0 that I can move around and a pole at the origin that I can do. And both of these have problems with it. Okay? And the problem associated with I don't have the pointer up. The problem with the 0 in PD control is it's a pure derivative, and that means you are amplifying high frequency noise. That is, ddt of cosine omega t is minus omega sine omega t. So the higher the frequency goes, the bigger it amplifies whatever noise is on top of that. All right. So this means that I'm getting sort of worse and worse performance as I go up in frequency, and that can be generally a bad thing. All right. Unless I happen to have a pure derivative measurement already. So for instance, if I am trying to control velocity and I have an accelerometer, all right, I'm measuring the derivative velocity directly, then I'm okay. I can go ahead and add that in there. All right. But if I actually am trying to do it synthetically and you're differentiating a signal, this is going to come kill me. So what we argued is that the way we want to do this is to roll off the action of this synthetic derivative with a low-pass filter, right? Higher up. And this is essentially when you combine the two together, we get what is called a lead compensator. Right? A lead has the 0 in front of the pole. Right? And what this does is it's basically I've just taken my derivative and I've just added to it a low-pass filter. That's all. Done nothing more than that. All right? And we also said the same thing was true. Now, if I go back and I say, okay, that was the problem. So the problem with a pure derivative was the amplification of high-frequency noise. The problem with an integrator is the other way. Okay? The integrator doesn't amplify high-frequency noise, but an integrator is problematic because without some kind of logic buried into it, it is difficult to use. Right? In that what it winds up doing is it works all the time to try to bring the error to 0. All right? It is by having something out here, all right, this is there's a very good chance that when this one moves this way, the other ones are gonna move the other direction. All right? So it's going to be destabilizing. And in order to get this over where some settling response is, I may have to crank the gain way up because this is going to be coming in towards this 0. All right? And in cranking the gain way up, I may have done bad things to the rest of my system. So this can be a relatively dangerous thing. So oftentimes what people do is say, well, that's great, but rather than put a pure integrator, let me put something that is close to an integrator. Let me move this off the origin, put it near the origin, but not on the origin. All right? And then what I have is I don't need any switch logic because it's not actually going to, it's going to do a lot to boost my gain at low frequency and attenuate it at high frequency, which is what I want. All right? So that gives me good DC tracking, but without a lot of high frequency noise amplification. All right? And we're going to get to Bode and we're going to see all of this sort of exactly.
Why do integrators create high frequency noise amplification when they do the opposite?
No. Differentiators increase high frequency noise. An integrator does not. An integrator actually attenuates high frequency noise. Okay. So what we said is that brings us, the lead compensator is essentially PD control, but one you can actually build. All right, that works well. And we've got the lag compensator, and the lag compensator does a zero close to the origin, but not on the origin. As I said, if it's a pure integrator, you need all kinds of logic to make it switch. And then we talked about the fact that if I want to put a branch of the root locus through any point, I can put that point down because I know where my time domain specs are. So I convert that to an S-plane spec. I say, okay, here's where I want my point. I calculate the phase at that point, and I figure out what I need to do, how much phase I need to add or subtract to get me there. Right? I'm looking for 180. And then I add my lead compensation, right, is the angle between the zero and the pole gets added to the root locus. All right? So now I have the degree of freedom, which is I can move the pole and the zero. As long as I keep the internal angle the same, I can sort of move it all the way around. All right? So I can put it anywhere I want, and I'll go through that point. All right? As long as I have the same angle, right? Depending on where I'm going to put it, it's still going to happen. Okay? And you can do all kinds of things. Now, the one that gets interesting, so there's a couple of things I want to show you. And let's see. The first one is, so one thing to be sort of careful of, if I have, this is sort of a general rule of thumb. All right? So if I have a system that looks like this, all right? Root locus on this one is going to be, well, let's see, the center of asymptotes is going to be here. I'm going to have three of them, 60, minus 60, there. All right? And this thing is going to go that way. These are going to go something like that and get on the asymptote. All right? So, and I say, well, okay, that design's not going to work very well. I can also put this on a 0 degree root locus. All right? And these two are going to do that. And so I'm going to have this one come in that way. These two are going to swoop and do something like that. And for a limited range of gain, I actually can find a stabilizing one. But one of the things that is careful, you have to be careful about here, is what happens, how fast does this one move relative to that one? So one of the common mistakes that people first learning this make is they assume that all poles move equally fast along their branches. And the answer is that they do not. Now, if you have a number of poles is greater than twice the number of zeros plus 2, all right? And this is sort of a rule of thumb. It only works when you're in this area. Let me just make sure I'm not going anywhere nuts here.
Is that statement true for poles and zeros?
What do you mean? The zeros never move, right? They're all very clear on that. The zeros never move. Right? The zeros are there. They're stuck. All right. So what you've got here is a so when my number of poles is greater than the number of zeros plus 2, what I can say is, roughly speaking, the center of the poles is going to be a constant. Okay? So what that means, center of poles divided by, in this case, n minus n, right, is equal to a constant. So what this means, for instance, these two are moving symmetrically. This one is moving here. So what this says is roughly that these two are going this way half as fast as this one is going that way. So if I wanted to get all the way over to there as my closed loop pole locations, I probably can't make it because that's going to put this one over here. All right. So this is roughly kind of a sense of balance. All right. So the idea is wherever these things balance before is also where they're going to balance afterwards. All right. So they're going to move, and they're going to move roughly in such a way as to keep these things balanced. It's a rough rule of thumb. It's not one I'm hugely interested in, but it's one that happens. Okay. So now, let's see. Now let's take a look at the notch. All right. So, and this works, by the way, if I have this thing of balance. If I have something that looks like a 0, a pole, and let's see. Let's do it this way, actually. Let's say I have my system here. It's slightly damped oscillations, and I say, okay, I'm going to fix this. What I really want to do is I want to add a compensator that looks like that, but, well, I can't do a pure one, so I'm going to put a lead compensator to make this work. And the root locus now is that, well, this one's going to come towards here. There's going to be an asymptote. The asymptote's going to be, oh, I don't know, let's say it's right there for fun right now. And actually, it's not going to be, it's going to be over here. Right? And those two are going to go out that way. All right, as I do that. Okay? So this still works where I say, well, how fast is this coming in versus how fast those are going out that way? It winds up going the roughly the same way. Okay. Now, a little note about pole zero cancellation. Okay? So, if I give you on an exam, now on an exam it's sort of different. On an exam the only criteria is, the easiest, fastest way I can come up with an answer. All right? And that's perfectly acceptable, but realize that isn't. Okay? I have a system that looks like this, and I say, here are your time domain specs, I want it, here's where I want my poles. Okay? And you say, okay, well, I'm going to do so with a lead. And what's the easiest lead I can come up with that will give me a branch that goes through that point? How about that? Okay? So I put this 0 right on top of that pole. Right? What's the root locus now? Well, these two go together. They split. That one goes up. That one goes down. Find my K. I'm done. No. Those are just, this is my zeta spec. Oh. Right, that's my zeta spec, and this is my omega n spec.
Okay, sorry.
Okay? So, hey, on an exam, this is perfectly legitimate. All right? No problem. All right? In real practice, okay, canceling a pole like this, what does this actually mean? All right? Now, it's subtle. What are the closed loop poles of this system? So I assume I choose my spots there. Where are the closed loop poles? Where are they? Come on. There's one there. There's one there. And there's one under that 0, right? I've got them like this. Now, when it's okay to cancel a pole with a 0 that you drop in is, well, remember that for a certain input to a certain output, the poles are always going to remain the same, but the zeros are going to change around. Right? So for a certain input, all right, I may get these three in a line like that. Well, in this case, that's kind of okay, right? Because, well, this is more or less at the same speed. It's nicely damped. Not worried about it. Right? The fact that I can't control this, but it has a mode that is nicely behaved anyway, means, okay, not a big deal. Right? But it can be a huge deal. So this is okay. All right. However, if I want to cancel something in here, all right, dropping a 0 on top of that, definitely not okay. All right. Because now I've got an unstable mode, all right, that I can't affect. I can't observe it and I can't control it. All right. Which means that if something else comes along and kicks it, it's going to grow exponentially. And that's going to be a bad thing. All right. So where is it okay to cancel poles with zeros? No, it's where you're okay with the response anyway. All right. So, you know, over here, definitely bad. Okay, that would be a bad choice. You know, up here in sort of the high frequency areas, probably also kind of bad. All right, because this means that this thing's going to oscillate quite a bit if something comes along and pings it. And maybe you're not concerned, but yeah.
Does that mean you can use zeros to choose which poles you want to move?
Yes, and in fact, that's exactly what we do with the notch. So we'll do that with the notch. I got to find my notch example, which is somewhere in here. I've been trying to find it, and I'm having some issues with it. But
So even though that response may not meet your spec, it's okay if it's from like far to the left anyways, because what are the odds when you set it at speed?
No. This, as long as this is sort of.
See, that doesn't meet spec now because it's not within your circle.
It's not within my circle. You're right. Okay. Now, in this, what it says is, well, my dominant response, when I've got on top of it, I actually don't see anything. So from Y over R, I meet specs because these are the only two that show up because this gets perfectly canceled. What it says is, well, Y over W or epsilon over V, which one of these, it's going to show up. But it's got a benign response, so I'm not terribly worried. Right. And then if I need to tweak it, I'll need to tweak it. And maybe that isn't such a great design. Right. But as a first cut, as I said on the exam, no problem. What I want to do is, you know, something in here may also be sort of a bad area, right? Because this may take way, way too long to catch up. And by putting a 0 next to or near a pole, all right, you're going to make sure that pole does not move, regardless of what you crank your gain to, all right? Because the zeros suck on the poles, and so it keeps it from moving wherever it's going to go quite slowly. Now, here's where we do our
question.
Yeah.
The original pole that's there is that actually in the plant? Then?
Yeah, the two red ones are part of the plant,
Gotcha.
and what I added was the green compensator. Okay. No problem. Now, we had back in, let's do the notch example. All right. So I had my mass. It was on a spring. It had a little itty bitty damper on it, and it had this little piston that I could put my force in. And we had a little camera that was reading out this. And what we wound up with was, we said, look, at first, here are our 2 poles. Okay, that was what they looked like, and if B is 0, then they're on the j omega axis. If B is, as B grows, they come in. But we said this didn't have much damping in it, and I said, okay. Now, originally we said, well, the first way we were going to compensate this was we're just going to put pure PD control. Right, PD control, you'll see, will, you know, now that you've drawn enough of these 2 orbit around here, splits, one comes in, one goes out, and we say, okay, that was our first cut design, and that was a good one. And we say, well, not so good in that I hopefully have made the case now that a pure PD control is not quite what we want. So we say, well, we're going to go, yes, we're going to actually put a lead controller in. And what a lead controller is going to do, this thing's going to have an asymptote something like there. All right. The lead, by the way, notice that the lead moves the asymptote to the left. All right. This is kind of important. All right. So lead is stabilizing. It moves the asymptotes to the left. So from far away, it's moving things into the left, farther into the left half plane. And what will happen is these will start on their same orbit, going around as this one comes in, and as this one comes in, it'll push the 2 branches away, and they'll wind up going up that way. All right? But as long as the gains I'm looking at are not excessive, all right, I can pick my spots, and I'll be very happy with my nice damping and my response where I'm okay with this. Okay, so this we said was our controller. And now we said, well, but wait a minute. There is a spring that connects your sensor, right, to your mass. Now we did it twice, right? The first one we did was we put a little mass up here, and we said, well, what happens with that one is it winds up with way up here, a pole and a zero, and that's okay. They sort of cancel each other out, all right? And life is okay. Yeah, that little spring is going to wumpa 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 wumpa. Little mass up there. When you ping this thing, it's pinging all around up there, but it eventually damps out, and life is okay. And we said, well, that's all right. But now what happened when we moved it, that little spring mass to be our sensor, i.e. now we're directly incorporating that, what we found was we had no zero up there, but rather 2 poles on the j omega axis far away. Bummer. All right? And we said, okay, now we have a problem. Okay? Because now, if I draw my root locus, okay, I'm going to draw them way down here. I've got those 2. I added my compensator that looked like that. And now I've got these 2 way up here. Okay? So, I've got 1, 2, 3, 4. Okay? Center of asymptote's going to be right there. And it's going to be roughly, right, there's going to be my asymptotes. Which means that this one's probably, this one's going to come in here. These 2 are going to do something like that. These 2 are going to do something like that. Right? Bad. Okay? So this is going to be, actually these 2 are they're going to start on their orbit. From close in, they're not going to change much, and then they'll do that. But these 2 are definitely problematic. Okay. So what do I do about it? I've designed my controller. I'm sort of happy about it. I kind of want to not mess that much with what else I've done, but I have to deal with these high-frequency, unmodeled dynamics I didn't know about before.
Put 2 holes maybe that are on the left-hand side, but near the holes.
So what we add is a notch. What does a notch look like? 2 poles down here and 2 zeros somewhere up here. Now, where's the right place to add the zeros? All right, what I'm going to do to make life easy to build, I'm going to make sure that these are on the same arc. All right, so my notch compensator is going to look like s squared plus 2 zeta omega naught s plus omega naught squared, where zeta is close to 0 but not 0, divided by s squared plus 2 omega naught s plus omega naught squared, which puts these 2 down here. Okay? I've added 2 poles and 2 zeros. I have not altered the asymptotes. Okay? Same asymptotes, same place they were before. I've changed slightly. I've moved. Now I've done some stabilizing because these 2 poles with those 2 zeros move the center of asymptotes that direction, right? Right? Moves it towards the left. All right? But I still have asymptotes. They're still going. Now, the question is, let me zoom in on this area right here. Okay? So I've got 1, 2, there, something here, and I've got my pole and a 0. I know eventually that 2 poles are going to wind up on 2 of these guys, right? But that's okay, because I'm not going to crank the gain up to infinity. All I need to do is find an intermediate gain, in which I can stabilize this. And we've said for low gains, right around here, I'm okay. Right? Things move in the direction I want, and I'm able to fix my system. Right? So, what do I want to do with that? What's the one thing I want to make sure I don't do with that pole? You don't want it to go right. So, what's the farthest away from right that I can do? Left. Right? So, I want to move the 0, right, in here, because I have a freedom of choice of where I place the 0. Yeah.
Can we assume that as far as the furthest distance over to the left it's going to go, it's going to be roughly about the distance to the pole?
No, you may not assume that.
Dang.
All right.
So would this be a sinister control?
No, this won't be sinister.
It's going to be sinister, but I mean,
Yes, I know. Io sono sinistoso. Notice which hand I have my my pen in. I've been called sinister for a long time now. That means left-handed in Italian, by the way. So, all right. So this now gives me a legitimate question of how do I place the 0 such that the departure angle of that pole is 180 degrees. Right? If I make the departure angle 180 degrees, then I'm okay. So what do I do? Well, we add up the phase. All right? So I'm going to look at this, and I'm going to say, all right, here's my phi departure. I've got this phi from the 0 here. Okay? And the way this is measured, if it comes out to be 0, I'm going to put the pole here. If it comes out to be positive 90, the pole goes down here. If it comes out to be negative 90, it goes up there. If it comes out to be 180, the pole goes up here. Right? But I'm going to move this pole around in the vicinity, all right, and cause this guy to go left first. All right? Whatever he's doing first, he's going to go left. All right? And that means that at least while I start cranking up the gain, it's doing the right thing and getting better. All right? And at least it's not getting worse. It's sort of the Hippocratic oath of controls engineering is, first do no harm kind of thing. All right? So I'm trying to do this. Now, what are the other ones? Well, I've got 90 degrees from that one, 90 degrees from that one, a pole and a 0, effectively 90, 99. So this is minus 90, minus 90, minus 90, plus 90, so it's minus 180. I've got 2 at 45 from this one because they're on the same radius, so that's going to be 45. Pretty damn close to it anyway. Let's call, I've got this angle and this angle, all right, which I'm going to measure. So I'm going to have basically phi minus phi d, because it's pole, right, plus the phi from the 0, plus all of this other junk, right, minus 90, minus 90, minus 90, plus 90, minus 87, that's going to be plus 87, minus 70-something, minus another 90 from the 245. So there's going to be stuff in here, all right, that adds that all up, is going to equal to minus 180 degrees. Now, I said, well, wait a minute. I want this to be 180, right? So solve for phi z, right? And it tells me where to place that 0. Bless you. In the case of this problem, I actually went through and I did it. And what we wound up with was that phi d was equal to phi z minus 85 degrees. All right? Which means, where do I want to put the 0? I want to be roughly at 180. Okay? Right. So this means at negative 95 degrees, which means that the 0 is actually going to go above the pole. So I'm going to do this. So here are my 2. I added my first compensator. I discovered I had these 2 unmodeled high-frequency dynamics. I added my second compensator, like this. And now, if I draw the root locus of this guy, we know that these depart at 180. And they button hook and come around back to there. And they're not going to move very fast, by the way, because there's a 0 very close to them. Okay? I'm going to have my center of asymptotes. I've still got 4. So this is still going to be doing something like that. All right? These 2 are still going to depart going this way, like so. Right, around. This one's still going to come in. These 2 are going to split and eventually do that. And these 2 are going to turn around and go that way. Right? But what this means is, for a while, all right, before this happens, all right, I have got a control that works. All right. Now, someone might say, well, why do it this way? Why not just land that 0 right on top of that pole? Just kill it. Right? I'm not particularly concerned about it anyway. It's just a little thing that's going wumpa, wumpa, wumpa. What do I care? Kill it. What's the danger if I just land right on top of it? Not necessarily something else bangs it.
You lose your angle control if you get too close to it. Small differences.
Okay, so there's one part. It becomes incredibly sensitive to how good I am at making that appear in the right place. The second thing is, what if I don't know perfectly well where this one is? All right?
Change over time because the spring is very level.
Exactly. Or, say this was a car I was trying to control, and my shocks get, they get old, right? The springs get a little, get a little, they start to decay over time, and they don't stay quite as stiff. Yeah.
This next brings me to a question. What if you've got essentially some sort of time dependence in your game?
Yep.
Your pole is going to wobble to a certain extent, and
Mm-hmm.
if it's on the same order, or that doesn't essentially mean your locus is changing in time?
Well, if your gain changes with a function of time, i.e., you have a mechanical system and it's losing its oomph over the years, it's going to change over time, and that means that you're moving along the locus. If the position of the poles are moving because your system is actually changing, it means the locus is changing. But again, if I move these to here, it doesn't change it all that much. All right? Yeah, okay, so there. They moved. All right? But not a big deal. All right? The ones you got to be careful about are the ones that are in sensitive areas. Right? So usually you spend a lot of effort on nailing down the ones that can be critical. But this brings up something which is a larger point, which is, okay, I've said this is up here, but really it can be anywhere within the circle. All right? This is sort of what I expect over the lifetime. All right? I want to be, if I put my 0 in too tight, okay, and it's supposed to go this way, but it's moved, I may now be sending it in the exact opposite direction. This is not a good thing. Right? This, would be the equivalent of, when my brakes get hot, then, bad things start to occur. All right? This generally wouldn't be a good design. So what I want to do, this brings up sort of the argument of robustness, which we're going to address much, much more in Bode, because robustness comes straight out of Bode, whereas it's not readily apparent in locus. What we're starting to talk about here is how do things change as I move them around. So the way to be safe with this is if you're going to put a notch in there, you put it far enough away that that no matter where this goes, you're still roughly 90 degrees away from it, right? So I just move this farther out, and I'm still going to suck it in. It's still going to go back to there, all right? So I'm still okay. All right. Now, solutions to an old homework. Now, here is one which is kind of an interesting one. Okay. I have a system which, let's start with, all right, before I do this, I have my system, I have my reference signal that goes in. I have my, let's call it K of S, G of S, comes out, I feed it back, and in I go. And I do this, and this is let me just make sure I have this one. Where is he? Not that one. Well, we'll wing it. All right, so G of S is 1 over S squared plus 1. So that gives me 2 right there. And I say, okay, I want my specs to be zeta 0.707, omega n equals 0.8. All right. And I'm going to, so if I look at this, here's my zeta 0.707 lines. 0.8 is going to be in here, a little bit like this. And I've given you a procedure of how we do this. Okay? So we can calculate the phase at this point. Right? I can find exactly this point. I can calculate the phase by adding both of those angles together, right? Summing them to 180 and saying, hey, I'm missing so much and I'm going to need a lead compensator. All right? And it's going to be a bit of a fat one, right? So to get enough lead to get in there. And it's going to look something like that, right, with this internal angle, right? And this is now going to have a root locus where this is going to go in like that. These two are going to hit here and then head on up to its asymptote. And life is going to be interesting. Now, I do this and I plot. Actually, I can even do this with just one. I can get rid of this one altogether. This actually appears sort of farther out here. I do all this. I can even say, well, I can bring this in up to the point where this goes effectively to minus infinity. So I'm just putting a 0 in. And if I do that, it's the simplest control I could conceive of that would satisfy my specs. And it's going to look like, so these are going to do that, essentially. Actually, no, these are going to come in. One's going to split and go that way. The other's going to go out that way. And I choose my gain to put them right on the 45-degree line. Right? In this case, my compensator K is going to look like 1.12 S minus 0.32. Okay? What's that? This is PD control, but this is PD control with something weird going on, right? Because my 0 is in the right half plane. Right?
So you did like negative feedback.
This is non-minimum phase. Now, so I do this, and hey, I've got zeta is 0.707, and omega n is 0.8. I have hit my specs exactly. This is a second order response. Life is good. Now, what happens if you think I plot y over r to a step input? Any guess what this will look like? So here's r is going to go up to 1. Right?
You got the wrong way first.
Actually, so what we expect to see is something that goes like this and settles in, right, with a 5% overshoot. That's the 0.707. We expect a certain settling time, a certain rise time. Everything is happy. What we see instead is something that goes like that. All right.
Because your A is pointing in the opposite direction, so the other term picks up.
Well, this is sort of a subtle point. Root locus, I've drawn this, which is essentially, this is the block diagram of a tracking response, right, where I want to track R. Root locus does not know that this is a structure, nor does it care. Root locus is only concerned with the placement of the poles of the closed loop system. So from any input to any output, I always have the same poles. Right? Root locus is fundamentally concerned with the system is at rest, I ping it, and what does the transient response look like? All right? So this response is going to occur, right, because there's 0 over here. Right? However, as far as the closed loop poles are concerned, there they are. It has 0.707 damping, and it has an omega n of 0.8. Right? It's not necessarily. So what if I put the 0 right on top, all right, of the origin? All right, I won't meet these specs exactly, but if I put the 0 right on top of the origin, and I hit this thing with a step, I'm going to see something that looks like this. It's going to spike up and go to 0 because it has no DC gain. Right? Which means, oh yeah, it's great at rejecting disturbance. Really fabulous at it. And it does so with a really nice transient. Okay? but the system is fundamentally useless. All right. Now, this is why we've been sneaking in these steady-state error requirements in all of your designs. Okay, this is a way to back in to what we've been doing with Bode. All right. And remember, I did this plot before where I said, look, I've got my input, goes in, here's my compensator, here's some sort of disturbance that comes in, my plant, my output, I have my sensor, which we're going to call 1, I have some noise, and it comes in, and it feeds back with negative feedback the way we're used to. And what we said was, look, y over r is kg over 1 plus kg. Right? This says, hey, for low frequencies, whatever frequencies I'm interested in tracking, i.e. I'm putting an r into, I want kg to be big. Right? So if I start plotting the magnitude of kg versus frequency, all right, at low frequencies, I would like it to be big. Okay? Why do I want it big? Because I want y to equal r. So if kg is big, then y equals r. Okay? The problem is, if I look at my disturbance, now this is also good, right? If I look at my disturbance, I wind up with g over 1 plus kg. So again, if kg is big, this is good, because this means I reject disturbances. Right? So again, this is good tracking, and this is disturbance rejection. So I'm happy about that. Okay? That's a good thing. Okay? Now, if I look at, however, y over v, I wind up with kg over 1 plus kg. Right? Which means that my noise, if I make kg big, it means my noise is also being amplified. Right? The same way I get good tracking response, I also get a noise amplification. Okay? So what I want to say is, well, okay, for certain high-frequency noise, I want to attenuate. Right? Remember that high-frequency stuff, the unmodeled dynamics? I want to knock that down. So at high frequency, I want kg to be small. Low frequency, I want it big. High frequency, I want it small. So this is noise rejection down here. That's rejection. Yeah, too close to the edge. There's noise rejection. All right, and also down here comes plant uncertainty. All right. So I want to knock it down up here, and I want to punch it up down there. So we're going to get to how we actually do this. Remember that root locus basically says, look, I've got 1 plus kg equals 0, so look for kg equals minus 1. Everything was satisfying this criteria. The problem is, 1 plus kg is in the denominator for every input to every output. Right? So, yes, that's very useful information. Right? It tells me all about the transient response. But it doesn't tell me anything about tracking, and it's important to understand that Bode, on the other hand, is concerned entirely with tracking, doesn't know anything about the transient response, nor does it care. Right? So the two are very complementary. You wind up using both all the time. Okay. So the Bode response says, look, I've got my G of S, and I want to evaluate the magnitude of G of S and the phase of G of S at S equals J omega. All right? So now what we're going to do is let's take a look at our first simple thing. Let's see. Well, we'll do that one afterwards. Okay. So we'll start with the simple one. I've got G of S is equal to A over S plus A. Okay? This should be recognizable as a low-pass filter. Single pole. and we'll see why. All right, so here is my S-plane. There's my pull at minus A. All right. So this distance is A, and I'm going to probe it from a point j omega. So what we've already established, let me call this L, and let me call that phi. Right. So L, right, which is nothing more than, so the magnitude of g of j omega at s equals, yeah, I've got that. The magnitude of g of j omega is nothing more than 1 over L, right? Which is equal to, so this is going to be omega. This is going to be 1 over the square root of omega squared plus a squared. Okay? All right, and I can see that from, there's L, omega, that's 90 degrees, so basic trig, there we are. Okay? And the angle of g of j omega is going to be the arctangent of omega over a. Okay, so what does that mean? Let's start off with on the real axis, so omega equals 0. At omega equals 0, right, the magnitude is equal to 1 over a. Actually, a over a, right? So it's a divided by a, right? So the magnitude is equal to 1. Let me put an a back in there. A over L, the way we've written it. Right? Because that just gets pulled out. Okay. So at omega equals 0, the magnitude of it is 1, and the phase of it is equal to 0. Okay? At omega equals infinity, really, really super far away. Okay? The magnitude of it equals to what? Right? The magnitude of it equals 0. And what about the angle? Is it 90 or is it minus 90, right? Right, because, sorry, there's a minus sign in here. Because it's a pole. If it was 0, yes, it would be 90. But it's a pole, so the angle is negative. So it's minus 90. All right? And what about at omega equals a? What's the magnitude equal? 1 over? Square root of 2. Okay? What about the angle? Minus 45 degrees. Okay. That looks familiar. All right, now, what if, so I can do this, right? For simple systems, I can get away with a lot about this. All right. So now, what if I have g of s is equal to a over s plus a times b over s plus b? Okay. This kind of makes my face go sad, all right? Because I was going to say, well, all right, this was easy enough for one, all right? But this is going to start to get kind of a pain. This is going to be too much work, all right? And as we both know, I don't like to do a lot of work. But I can do this, and I can say, hey, wait a minute. This one is, in fact, so I'm going to evaluate these at s equals j omega. This is going to turn into m1 e to the j phi 1, and this one is going to turn into m2 e to the j phi 2. They're both just complex numbers, right? So together, they're going to be, so if I want the two of them together, this is m1, m2, e to the j phi 1 plus phi 2. Right? So now I say this is all fine and dandy, but it's not getting me quite where I want to go. Right? So rather than plot the magnitude of g versus frequency, right? So the magnitude of g versus frequency, we said it starts at 1. all right, it's going to go to 0. So, and in the middle, at the frequency A, it's going to be 1 over square root of 2. Right? It's going to do something like that. All right? And I say, okay, so I can do this for 1. I can do that for G1, right, for that one. I can do it for G2, right? And, well, you know, I have to multiply them. And, you know, as far as I'm concerned, multiplication is hard. Right? So, what's the obvious answer to get away from multiplication? Log, right? So we say, no problem. I'm going to plot log of G1 here versus omega. And I'm going to find out something that, you know, get something that changes here. Right? In fact, since this is going to 0, this is just heading down. Right? And now, if I plot both of these on the same graph, I just add them together. Ta-da! And if I plot, so if I plot log of G1, I add it together. If I plot just the phase angle, not the log of the phase angle, I add those together because that's an addition. And I'm cooking on gas. Right? So far, I'm doing okay. Now, let's make sure I haven't... right, that one is done. Hopefully, you guys can see where we're going with this. Now, the big problem, of course, is... Let me just make sure I've got nothing here that I... that. Okay, that one's done. All right. I have a design example we can do. We'll do that one a little bit later. Let's. So far, we're okay with this. Now, I've suggested why we do log on the magnitude side, on this side of the scale. Now, there's a reason we're going to do log on the frequency as well. Okay? And the log on the frequency we're going to do is because we're going to turn these nice curves into straight lines. Okay? And, you know, I can draw straight lines. So that makes it easy. Right? So I'm going to go from something hard to something easy. Now, the way we justify this is pretty easy. Let's assume that G of S is equal to some S to the N. Okay? So I'm going to substitute S is equal to J omega. So I've got G of S is equal to S to the N is equal to J omega to the N. Okay? Now I'm going to take the log of the magnitude of G of S, right, is going to equal to the log of omega to the N, where it's going to be equal to N log omega. Right? What's that? Well, when I'm taking the magnitude of it. Right? So, if I plot it versus log omega, then there's my slope. Right? If it's 1 over S squared is G of S, then my slope is minus 2. Right? If it's S cubed, then my slope is plus 3. Right? In the log-log domain. All right? Now, let's do a fun design example. That one came before this one. And then we're going to start plunking down. All right, here's our example. I've got G of S is equal to 1 over S squared plus S minus 2, which I've conveniently already factored to 1 over S plus 2, S minus 1. All right, so here is, very quickly, I've got a 1 a -2. I'm going to have a setter of asymptotes at 1/2, -1/2, and there's going to be my root locus. Okay? And I say, look, I want a closed loop pole at -2 plus or minus 2j. Okay? That's where I want my system. All right? So I say, well, let's take a look at it. And I say, all right, so this is at that's at -2, that's at -1, and I've said this is where I want my closed loop poles. Okay? So that's 2, this is actually 3, that's 2. Right? So I calculate the phase of all of this, and I've got, let's do it. So the phase of my desired point, right, is equal to, well, that's 90 minus 90 from that pole. I've got, this is going to be minus 180 minus arctan of 2/3. Right. Plus some compensator, which I have yet to figure out what I'm going to put in there. Right, it's either going to be a lead or a lag. Right, is going to equal to minus 180. Yeah? The 180 minus that angle, right, is that. Right, so if I do this, I wind up with minus 90 minus 146.3 is equal to minus 180 plus my compensator. And I get that, therefore, phi compensator is equal to 56.3 degrees. Okay? So,
shouldn't that be negative minus the degree of
let's see. Well, it's going to be this, and I'm going to figure out what I need to add my compensator to get it back to 180. Right? Because I'm going to come up shy of 180. Right? So I'm just going to leave it. I'm just going to leave it where I'm going to look to see what I'm missing. How much do I need to add or subtract the phase to get to 180? Yeah? So I calculate it out, and it says I need to add 56 degrees of phase. So how do I add 56 degrees of phase? Well, what do I use? Come on, people. There are only two choices here. A lead, right? Lead adds phase, lag takes phase away. Right? So, yeah. I need this to be 56 degrees. Yeah.
Yeah.
That means that you're adding in.
Right. That means you're adding in phase. So, by the way, this is where we do it. Okay. So I need to add in 56.3 degrees, which means this is the angle between that 0 and that pole, and I can move it around. So the question is, where do I move it to? Well, if I've got this one, that's that. Let's say I put it I place the 0 at -1. Okay? And then this is where I want to be. And then I can actually sort of say, well, from here I need 56 degrees, which puts the other pole there. Okay, so there's my compensation. So now if I look at the root locus, this one comes into that. These two wind up going this way and heading off to their asymptote. Okay? And sure enough, I blow right through there. Now, So, by the way, sort of working this out comes to be that the compensator, K of S, looks like S plus 1 over S plus 3.14. And I have to find the K in order to do that. And I can figure out at which point I cross in and become stable, right? And I can do this using Ralph, for instance. I can also, there's lots of different ways I can do it. And what Ralph says is as long as K is greater than 2p, wherever I place this pole, right, then I'm stable. All right. Now, the problem is, yes, I'm stable, but I'm actually pretty damn slow, right? Because remember, this guy, he's going to be stable, and he's going to slowly crawl in. In fact, at the point, at the gain, I can also calculate my gain at this point, right? So what is my gain? My gain is going to be the product of the poles divided by the product of the length of the zeros, right? And this gets me about 7.43 if I do it. And what that means is I've got a this one, where that winds up, the closed loop, is at 0.142, right? So, very slow. Which means I requested a snappy response with a nice overshoot specs, and I got them on the transient, right? Which is to say that there's this e to the 0.142, and it'll get there, and riding on top of that, I've got my nice, beautiful, snappy response. Meaning that I've got, it climbs very quickly, my rise time gets me to there, right? Has a nice little bit of overshoot, and then it starts tracking that exponential growth. Right? So this guy is bad. He's not horrible in that you still eventually get there, but it isn't necessarily what you were looking for. Right? The response is dominated by this one. So what you do is you iterate the design. And you say, well, okay, let me come to a different one. Let's see what happens if I do another type of design. I know that I have to add 56.3 degrees to get me through that point. Okay? Here's my original root locus. And now I'm going to say, look, I'm going to put my 0. I had my 0 at -1. That didn't help. Now I'm going to put it almost on top of this at -1.9, which winds up sticking this one. So this is at -1.9. This one goes out to 4.69. All right. And this now, if I work out where my my closed loop poles are, I get -2 plus or minus 2j, which is what I wanted, and then -1.697, which is better. Okay, I've pulled in this way. These two come together, they split, they go up, and again they go right through my point, and I'm happier with this. Okay, I am. I think this is good. Okay, and now I say, well, okay, but what if I can get better? All right, I can keep sliding the 0. I can go out past this point. I can go. Now I can do something where I put my 0 here. Right, I'm trying to get to that point, and now this is 56 degrees in here. And now, for my root locus, this one's going to come in. These two are going to split and do that. And I say, hey, now I'm at -2 plus or minus 2j, and the other one's at -2.352. All right, so I'm getting better. My k, by the way, is going up. My k at this point is Oh, on this last one, I wound up with K here was equal to 12.0908. And here I had that K is equal to 14.0654. Any reason why it's taking me larger and larger gains to get there? I'm moving things further and further away, right? That's requiring me to put more gain in. And now, hey, what about if I say, look, I can move my pole all the way out to infinity, all right? And I say, well, I'm just going to be picking some candidate things here. So that's at -1. This is at, sorry, that's at +1. This is at -2. And I say, hey, I want to put my 0 at -4. Right? And if I work out what the angles are, right, this is the angle to my 0 is 26.56 degrees, which means that the angle to my pole works out to be -29.74 degrees. And that is not possible. Right? I can't get enough lead. Right? I've moved this one too far out. Right? The only way I can get to, the farthest I can get to, is where this is 56 degrees below the horizon. Right? And that's moving the other pole all the way out to infinity. And back to pure PD control. Right? Which we've told you is a bad thing to do, but, you know, hey. All right, so if you also, what is, by the way, the most lead that you could ever get with a pole 0 pair? Right? How much lead can I ever get? 180, right? Right. Practically, you'll discover that about 50 to 60 degrees per pair is about all you can actually do. All right? Things start to get, because it's basically as soon as you get to 90 degrees, right, you're pushing this one into the right half plane. All right? For any kind of thing, and we've discovered that doesn't really work well. is s plus j omega. All right, so again, for omega is much less than a, this looks like a. For omega is much greater than a, this looks like s to the 1. So this looks like a here, log magnitude, log frequency, and then it's going to break with a slope of plus 1. Right? Okay, so we got those two. We've got what s to the n. Let's do it. Right, and that's, so this is a 0 out there. Right? And we've got an s to the n, right, evaluated at j omega. Right, so this is going to equal to j omega to the n. Right, and so the magnitude of it is going to equal to omega to the n, or if I take log of both sides, I've got that the log of the magnitude is proportional to n log of omega. All right, so it's straight lines. And so now we sort of, what we're going to do is we're going to take this whole thing and we're going to build it up piece by piece and keep adding all the different pieces to it until it all begins to make sense. And then we're going to find that there's a couple of approximations here that we use for what the exact breakpoints are and the frequencies at the breakpoint. And with just a few little sort of hand waves, we'll be cooking on gas. So let's look at something particularly nasty. Let's say I have k s plus alpha s squared plus 2 zeta omega n s plus omega n squared divided by an s to the n s plus b. Was this an a? That was an a. S plus b and an s squared plus 2 zeta omega 2 s plus omega 2 squared. All right, so remember that s always appears with integer powers. It never can do anything else. All right, and basically I'm going to go term by term and do everything. So let's start the first one. Okay. So one of the things is in the book they use this Bode form. And the Bode form makes it look like this. They've got k tau 1 s plus 1 s over omega 1 squared plus 2 zeta 1 s over omega 1 plus 1. And s to the n, let's see, tau 2 s plus 1 and s over omega 2 squared plus 2 zeta 2 s over omega 2 plus 1. All right, all they're doing is dividing through by omega. And
S over omega 1 squared next to zeta?
no, that should be only an s omega 1.
Well, then omega 1 disappears. Otherwise, because it's zeta times omega. Yeah.
Right. Yep.
What's the tau then?
The tau is just 1 over a.
Oh, right.
And, 1 over b. So it's just the frequency at which it breaks. If you do this when you're evaluating it at s equals j omega, it makes a little bit more sense, but hey. Let's break this up and do it in parts. So the first one is k. Okay? So what is the magnitude of k evaluated at s equals j omega? It's just equal to k. Right? So here's log frequency. Right? K. Right? What about its angle? What's the angle of a constant? 0, right? Okay, so there it is. Right? So the gain is easy. If I change k, this is moving up and down. Right? if k is equal to 10, this comes out at 1 on the log plot. Right? Yes? Everyone happy with that? Okay. All right, so now that was one of them. The next term we'll do is we'll take s to the n in the denominator. All right. So again, this is just going to be the magnitude of it is just going to be equal to a n log omega. All right. So in this case, we have it in the denominator, which means this is going to come down with a slope of minus n. Right? Coming down like that. It's going to pass through 0 at what frequency? Right? So 0 has a gain of 1. Right? The log of 0 is 1. Right? And what frequency is it going to pass through that? S to the n. When's the magnitude of j omega to the n? 1. Well, what's the magnitude of it is just omega to the n, right? Right? So, well, but this is log frequency, right? So at log omega, this is going to pass through at 0, so that means that it's at omega equals 1. Right? So this has a gain of 1 at a frequency of 1. All right? Okay. What about its phase? What's the angle of this?
90.
If n is positive, it's 90. What about if n is 2? Anywhere on the j omega axis, I'm talking about, so if n is 2, I've got
Minus 180.
zeros. Positive 180. Right? This is going to be, so the phase of this is always going to be n times 90. And it's going to be constant over all frequencies. Right? So that means that the phase of this guy, all right, is going to be at, in this case, this is going to be minus 90 times n, right, versus log omega. Okay?
Which we can figure out because you take a second derivative, you get a minus sign effect. It's the same thing back.
Or you can just do it graphically. I mean, I'm going to sample at this point. Right? So that's 2 times 90. Right? They just add. All right? So, now we're going to take the, we'll take this one. So the third term, we're going to have tau s plus 1 evaluated at s equals j omega. All right, so this one is for omega tau is much less than 1. The angle is equal to 0. Omega tau is much greater than 1. The angle is equal to 90 degrees. And at omega tau equals 1, then the magnitude is square root of 2, and the phase is 45. So this is just the same one. All we did was we plotted it. It's the same one we had before. This is just an s plus a in the numerator. All right, and we said, well, it's got a gain of 1, right? So that this puts it in a normalized form. All right, so the same thing as having a over s plus a, or s plus a over a. Right. They just said, well, okay, so that's 1 over a, and that's 1. Yeah. Just normalize it, no big deal. So in a log domain, this is 0, right? And then it hits, and it breaks up to a slope of positive 1. The angle that it does, right, is it starts at 0 degrees, it's at 45 degrees here, and it's at 90 degrees way out here. Now, there is a question of this obviously isn't a clean break. It does something like that. And this does something like that. And so there's a question of which straight line approximation to use right here. Okay. So there are two different ways of doing this. One is to match the slope. One is to use a least squares fit. So I can use a least squares fit and say, well, okay, to first order, all right, we can do a least squares up here. The other one is to say, well, I'm not really concerned out over here so much in terms of least squares, but instead I want to match the slope at the center point. So these are two different ways of doing it. If I do it, let's see.
Least squares fit for just taking all the data, doing least squares.
Yeah, so I'm going to say, look, I can actually tell you exactly what the phase is at any frequency. Right? So I'm just going to sample all these points for these 3 straight line segments versus the actual one and give me a least squares through it. Okay? So, because what is phi? So phi is arctan of omega t, omega tau rather. All right, and what I'm going to take is d phi d log omega tau, and I'm going to evaluate this at omega tau equals 1. And this is going to be, let's see, ddx of arctan of u, so x is equal to log of omega tau, u is equal to omega tau, and ddx of arctan of u is 1 over 1 plus u squared du dx. So if I do that, I get that du dx is equal to e to the x is equal to 1, and I've got log of omega tau comes out to pi over 2, since it's 1/2, right? So the slope at the center should be 1/2, right? So I match it, and I'm going to get that omega tau is equal to e to the pi over 2. And what all of that means is we come up with a straight line that looks like the following. Oops. Got used to drawing root loci there. So here is my 45 point. Log omega phi. Here is 45, 0, and 90. And the breakpoints are at 1 over 4.81 omega tau and at 4.81 omega tau. Right? And if you do that, right, because this is, if you solve 1/2, so the thing you're trying to solve here is the 1/2 is equal to pi over 4 log omega 1 tau, and that gives you that you get 4.81. All right, 4 omega tau. So if you do this and you wind up solving this, it's roughly at 1/5 and 5 times the frequency. All right. Now, if you do it at 1/5 and 5 times the frequency, you get an error. And the interesting thing is, what error do you get? This has a slope of 1/2 at where you draw this point, which is where you wanted it to be. So we've matched the slope of the center point. And we've got an 11-degree error at the breakpoints. Right? So once you know that, you say, hey, 11 degrees up there. I now make a smooth line that goes through, and to far more accurate than you need it to be, there it is. All right? So sometimes it's good to know that you're 11 low and 11 high from where the asymptotes are at the breakpoints. All right? And that you're at a slope of a half right there, but that's really all you need. Okay? So now, we've done, how are we doing on time? I got enough time to do one more. All right, so what we're left with then is the second order terms. All right? So I've got s squared plus 2 zeta omega n s plus omega n squared, right, evaluated at s equals j omega. And I'm going to rewrite this as s over omega n squared, so I'm just normalizing frequency, plus 2 zeta s over omega n plus 1. Again, evaluated at s equals j omega. So for omega is much less than omega n, right, then the magnitude of it is equal to what? Right? That's 0, left with 1. Okay? What about the phase? 0, right? Okay? Now, for omega is much greater than omega n, all right? Then essentially the magnitude is going to look like omega over omega n squared, right? And the phase is going to look like 180 degrees. Now here comes the fun one, right? What happens at omega equals omega n? So I've got j omega over omega n squared plus 2 zeta omega n over j omega n over omega n, right, plus 1. Right? Well, this is going to be equal to minus 1 plus 1. Right? So those two kill each other. All right? Which means I've got 2 zeta of omega over omega n times j. All right? Well, what's the phase of that? Okay? Right? So the phase of this is equal to 90, right? What's the magnitude of it?
2 zeta.
Careful.
I thought omega was equal to omega.
Well, okay, so this is in the numerator, right? So the magnitude of this thing is going to be,
Oh, 1 over that?
now it's 2 zeta, so, but what happens if zeta is undamped? Right? So, if I plot this, right, I'm going to have it, it's going to start at low frequency, right, at a magnitude of 0. That is, the magnitude is 1, so log of the magnitude is 0. Okay? I've got my omega n, and I know that far away from omega n, I'm going to be going upwards with a slope of plus 2. Right? And what's going on here? Right? If I have low damping, this one's going to go like that. If I have no damping whatsoever, if those zeros are on the j omega axis, those are going to go all the way to a negative infinity. Right? And by the way, for the poles, this is just going to flip. Right? So it's going to go up. Now, one of the things we'll do is we're going to match the peak. All right. And we're going to find the peak magnitude and the spot at which the slope is positive 1. All right. So what you find is omega r is equal to omega n square root of 1 minus 2 zeta squared. All right. And that's the point at which this has a slope of plus 1. Right? So once I know that, all right, I now say, all right, look, I've got a couple of different things here. I've got the fact that it starts out at 0. Here's omega n. And here it goes up at plus 2. Okay? That's omega n. All right, and I know that this height here is 2 zeta, and that at this point here, which is omega r, is equal to omega n square root of 1 minus 2 zeta squared, and the slope is minus 1. And now all I do is I say, okay, well, fare that in, right? Match the slope here, and then off you go that way. All right, so we're about out of time, so we'll do this in more excruciating detail later.
Sorry, I'm getting lost over these graphs. Can you put that graph up again?
This is the log magnitude of s squared plus 2 zeta omega ns plus omega n squared. And right, this is the versus log frequency. All right. So this is, I'm taking something that has 2 zeros, 2 complex zeros, right, which are zeta and omega n away, and I'm probing them with an s equals j omega and moving along the axis. This is what's going to do. This is what's going to happen.
Was it doing that before?
Oh, so this is the resonant point.
That's the resonant point.
Right, and what's happening is you're getting, so think about this, if I have my zeros on the j omega axis, I'm going here, right, I'm moving up along. When I hit this point, I've got 0 response, I'm on top of the 0.
Okay.
Right, and therefore this goes zinc down to infinity. I put a sine wave in at that frequency and I get nothing out.
Okay, so we were having something, so this is only if we, you were saying this is only if we damp the thing though?
No, well in the case, this is if zeta goes to 0, right, you can see it from a graphical argument, right, so here's my 0 and I'm moving along this place here. Remember that the magnitude is nothing more than this distance away. Well, as I come here, that distance gets a lot smaller.
Right.
And then it gets bigger again.
Okay.
So I'm coming along, the distance gets smaller. Now it gets bigger again.
This is the frequency of our input.
That's correct.
Right. Okay.
Right. So that's the frequency of going in, climbing along the j omega axis.
Okay.
All right?
That's your own fault.
We nominated him. He didn't nominate himself. There are other people.
All right, let's see. This is going to be...
Ian wanted it. Aaron wanted it. Congratulations.
Why are congratulations in order?